Nice to meet you, all of the guests. Welcome to the session of the problem solution using the ProCAFD software tools, which the topic of this session is the webinar 1.2 process design stages. Okay, so in this presentation, it will be divided into two parts. The first part will be the presentation part, which will be presented by me, Chakapat Kongjan, and the next part is the demonstration part, which will be presented by Kontonok Udomong. So as we discussed yesterday, that there are three stages of the ProCAFD software, which the first stage is the synthesis stage, which the synthesis stages has already been presented in the last session. And in this session, we're going to present the design and the analysis stages, and the innovation stages will be presented in the tomorrow session. So the design and the analysis stages has consists of 4 steps together. The step 6, the design, process design, the step 7, the rigorous simulation, the step 8, the analysis of the econ, the life cycle analysis, the sustainability and the safety, and the step 9 is the overall summary and the target for the improvement definition. So first, let me tell you the input and that the user need to define and the output that the program will generate it step by step. Start with the step 6. The selected alternative from the step file that I have presented last time will be in the step 6, and the ProCAFD will calculate the mass and energy balance based on the symbol model, as well as the decision variable and the operational design. So in the step 7, the rigorous simulation, the program will use the information from the step 6 and generate the alternative model in the commercial simulation software, such as the Pro2. Then in the step 8, the analysis. In this step, the user need to import the generated report from the simulation file, and then the program will evaluate it 4 sets of analysis: the econ, the sustainability, the LCA, and the safety. Then after that, in the step 9, the overall summary and the target for definition improvement. In this step, the program will use the information from the previous step and summarize it in terms of the energy consumption, the utility cost, and the footprint. So in this step, we can see at the information and we can point out the target for the definition improvement. Last time we have read the step 5, the ranking. In this step, the user need to select one of the alternative and then click next. For the step 6, the design and the analysis. In this step, the selected alternative, one or more, will be presented here in this table. In this step, the program will calculate the mass and energy balance based on the simple model. In this step, some of the design parameters need to be fixed, as Professor Rafik and Professor Mario has already explained in the lecture. Then after that, we will click next. In the step 7, the rigorous simulation, the program will use the information of the mass and energy balance, as well as all the required design parameters in order to generate the simulation file, which, let's say we will select the Pro2 option. So the ProCAFD will generate the Pro2 file so that the user can modify the process simulation. And after that, we click next. In the step 7, the user needs to import the generated report of the simulation files, and then the program will perform 5 sets of analysis, including the econ, the capital and the operating cost statistic, cumulative cash flow and economic evaluation, the sustainable, including the sustainability indicator, the life cycle assessment, including the environment indicators of the inlet and outlet stream, the footprint, which include the ecological, the border, and the carbon footprint, and the safety, which include the chemical and the process inherent index. Then for the next step, the step 9, the overall result and target for definition improvement. The program will use the information of the analysis from the previous step and then overall summarize it in terms of the utility cost, the energy consumption, and the carbon footprint. In this step, we can see the information and then we can point out the target of the process improvement. For example, the compressor, the distillation column, the heater, and the cooler for the further heat integration and the process optimization. Like I presented before, the HDA case study needs to be carried out in order to give a clearer picture of how the program works. So the task of this process is to produce benzene from hydrogen and toluene. From step 5, the user needs to select one or more of the alternative. Then let's say in this example, we selected the alternative with the lowest energy consumption. Then we will continue for the further step 6 to the step 9. Then for the step 6, in this step, the user needs to click on the mass, click on calculate. So the ProCAFD will calculate the mass and the energy balance based on the simple model such as the mixer, splitter, and the reactor. The operating conditions such as the pressure and temperature of the outlet stream will be estimated from the process group information. Then after that, we click next. For the step 7, the regular simulation. In this step, user has the option to select one of the commercial program. Let's say we selected the option of the Pro Tool and then we click generated. Then the software will generate the simulation files, which the flow sheet of the generation file in the Pro Tool is in this picture, which is the flow sheet of the HDA process. Then after that, we click next. Then for the step 8, in this step, the user needs to import the generated report from the simulation file. Then the program will evaluate 5 sets of analysis that I have mentioned earlier. Let's start with the first analysis, the economic analysis. So for the first step, the ProCAFD has the function to export the econ file to the external. Then the user can modify the econ file and import it back to the ProCAFD. And after that, the program will analyze 4 sets of the economic analysis, including the raw material and the production, the equipment and the utility, the capital cost and the operating cost, and the economic evaluation. Then for the next analysis, the sustainability analysis. In this step, the ProCAFD will calculate the production rate, the water required, the water generated in the process, and the energy consumption. So the user can look at the number in this bar. Moreover, the user can look at the sustainability indicator in this table. Then after that, we click next. For the next analysis, the life cycle assessment of the LCA. In this step, the user can look at the number of the LCA indicator, which will be presented in this box, in this table. Then after that, we click next. The next analysis is the footprint analysis, which Pro Tool will generate 3 types of the footprint. The ecological footprint on the top, the table on the top, the water footprint, and the carbon footprint. So on the top, on the table on the top, the user has the option to choose the area or the country, and the ProCAFD will generate the ecological footprint based on that area. In the same way, for the water footprint, the user can also choose the area, and the ProCAFD will generate the water footprint based on that area. For the carbon footprint, the program will generate the carbon footprint of each unit based on the utility source that the user has selected in this box, and the carbon footprint data will be shown in this box. Then after that, we click next. The next analysis is the safety analysis. In this step, the user needs to select which reaction is the main reaction, which reaction is the side reaction. User need to select the construction material, the pressure, and the temperature. Then click calculated, then the ProCAFD will generate the chemical inherent safety index and the process inherent safety index in this box based on the Dow chemical safety index method. Then after that, we click next. Now, for the step 9, the overall summary, the ProCAFD will use the information of the analysis from the previous step and then summarize the overall information in terms of the utility cost, the energy consumption, and the carbon footprint. In this step, we can see that the unit which use the high utility cost is the compressor, the heater before the reactor, and 3 of the reboiler. The unit which has the highest duty is the cooler after the reactor. But since the cooler don't require energy, so it has low utility and it don't emit the carbon footprint. And the unit which emits the highest carbon footprint is the compressor. So now, from this information, we can set the target for the process improvement by doing the heat integration and the process optimization on this in order to reduce the operating cost of this unit. For another case study, the separation of alkane component, which the task is to separate the alkane compound. So I will skip some of these steps so we can catch up with the demonstration real quick. Then for the step 7, we can generate the simulation file by, let's say we click on the Pro 2 option and generate it. Then the program will generate the Pro 2, the flow sheet of the alkane separation is in here. And after that, we click next. For the step 5, the analysis, in this step, the user need to import the generated report of the simulation, and the program will analyze 5 sets of analysis, which I mentioned earlier. These are the results of the economic analysis in the alkane separation process, as well as the analysis of the footprint, which consists of the ecological footprint, the water footprint, and the carbon footprint. So now I will lend this presentation to ProCAFD demonstration by Kontano.
Hello, everyone. I'm Kontano Udomwong. I am delighted to be here to give you the demonstration of the software. So first, I will open ProCAFD. Okay, so turning now to the case example application of ProCAFD. According to the HDA study that Chakapat have present, now I want to demonstrate the ProCAFD software. So first, let's open the server HDA case example at the same. So from the last session, I have shown the step of the problem definition that user insert all other information by defining a compound, the inlet and outlet stream of the process, and the reaction data for the process. Then I will click next. Before we continue, I would like to have the live calculation. So I will go to setting tab and click for auto calculate. So it will recalculate every time that we change the step. So next is step 2. The objective of this step 2 is to generate the information that needed to perform a mixture analysis. During this step, the 5 compounds will form the 3 pairs of compound and will calculate the azeotrope, deuteratic point, and driving force of these And then the data will calculate the binary ratio of the system. And then this ratio will lead to the feasible process operation technique. So here is the azeotropic data of each pair, the driving force, and the eutectic data of each pair that I have shown before, and leading to the binary ratio metric table. And this property will lead to the feasible separation technique. And next is the process group selection. So in this step, I have mentioned that there is 3 types of process group, which is inlet and outlet stream, depending on the problem definition that user have given. And another is the reaction process group. And lastly is the separation process group that will be considered based on the feasible separation technique in step 2. And this is all amount of the process group that the software have generated. Next is step 3B. So in step 3B, the designer will provide a special constraint if they have any. For example, if I only consider the distillation unit, and then click next. So in here is we only have the distillation and fetch process group, and the flow sheet will be generated. And it also have the view button available to generate a simple flow sheet and generate the superstructure by super O. Okay, and next to step 5, all the feasible projects are ranked in terms of the performance criteria, no matter the energy of consumption, the carbon footprints, and the product recovery. User can rank it by double-click at the column, and the alternative will be arranged according to the energy consumption index. So in this step, I will select the one which have the lowest energy index value. Okay, and then I will go to next step. With the flow sheet that generated in the earlier step, step 6 will establish the mass flow rate for all of the compound in all of the process stream through a mass balance by using the simple mass model. So I will click calculate here. After click this button, ProCAFD will set stream process condition, temperature and pressure, and the calculated mass flow rate of each compound will be assigned and calculated in every single stream. This step also allows user to compute the enthalpy of all stream by clicking energy balance here. And in this step, we will be using the state of stream, no matter it is the vapor or liquid. And the stream enthalpy, the energy demand of every unit operation in the process, and the simple process simulation model will be calculated. So here is the data for the energy balance and the enthalpy data of each stream. And then it also can specify the temperature and pressure for all equipment. Finally, the decision variable. Yeah, so in the decision variable, the data is initially calculated based on the saturated vapor and liquid data. The calculated temperature and pressure will be calculated through dew point and bubble point of the compound. For example, if the flash unit in here, it will define by using the dew point for component A and B, and the bubble point for component C and D. Also, in this process, the heat exchanger are needed, and the outlet temperature will be set in here. Okay, and next is the operational design. So in here, for the distillation column, the column number and order design parameter will be given. Also, the feed top, bottom product, and the feed tail location will be located in here. So from all of these steps, the reaction conversion, separation factor, stream temperature, and pressure will be given. Also, the design parameter for the unit operation will be used in the regular simulation at step 7. After step 6 of ProCAFD helps to determine the equipment design parameter, then in step 7, the software will launch the internal and external process simulator that can perform the rigorous process simulation for selected process flowsheet. In here, there is Pro 2 and Aspen parts available. So today I will show you the example to generate the flowsheet through Pro 2. So during this step, the software will show the flowsheet that transfer to Pro 2. It will create the Pro 2 input file and launch the simulation. And this is the initial flowsheet created by Pro 2 by ProCAFD. And then I will click run.
Okay, so let me just add here that the flow sheet that you had seen in ProCAFD has been transferred to Pro 2, but a lot of the commands in Pro 2 have been used, the default commands have been used. So the simulation at this point is not very efficient. You will see that Concanoc will have to press 4 times to run. We could have increased the number of iterations, but we took all the default values in Pro 2 to let it do what it would do with respect to the default values. But what we will show you afterwards is that without changing any design parameters or anything else, we just improve the calculation sequence and the convergence criteria and things like that, and then the file operates much better. So we want to show you what is the original and what is the improved version. And Pro 2 here is converging for all the streams. That's why all the streams were red and then they became blue. So now Concanoc can take over and explain the rest.
Okay, so next I will open the Pro 2 file that we have modified. So in here, so
and the modification is not modifying the design, it's just modifying some of the commands.
Yes, and in here I will try to restore input data. So the data will be refilled again and then click run. So in this example, in this the modified flowsheet, you can see that it can be run very easily and fastly than the flowsheet that the ProCAFD can generate it.
So we are trying to find out how to use our given criteria rather than use the default criteria in the simulator. Okay.
So yes. So here we already got the flowsheet that are completely run. Next step will be we will export the output result of this flowsheet by using the Excel file format. User can do it by click output here and click generate Excel output. Then select the directory to import this file and click save. And it will take some minute to read writing of the data. Okay, so now the result will be in this file. I will close this one and close the flowsheet. And next, so in step A, using the simulation result Excel that was exported from the Pro 2 and the equipment sizing parameter, the software can read the stream summary by clicking import here and select the file that I have saved recently. Yeah, and the software will read the stream of summary data like the condition, mass, or mole flow rate of each stream. Also, the important equipment data is import, like the utility required, no matter the heating duty, the cooling duty, or the electricity utility of each unit. And this information can be used in the further analysis that I will show you. So here is the stream summary and the utility summary. It also gives you the detail of the unit description here. Okay, so after all of the data are imported, the analysis step can be started. First is the economic analysis. So all of the stream and equipment data will be exported to our economic calculated at 2 or econ. By writing the input file for econ2, and then user need to give the necessary data, cost data, and the sizing parameter. And then using the tool to calculate all of the cost data and import the input file back to the ProCAFD. So in this case, I already make an input file for the HDA case example already. So I will click import input file here. So normally the input file will be generated in this by this software, but there are some cost data that user have to manually insert in the input file. Then I will select input file here and click open. And then when we already import the input file, we can click generate econ output file here. So this is the macro econ tool. And the directory of the file will be indicated in here. I will just click load file, and the econ tool will read all the data. So here, for example, it will have several forms of each equipment that are in the process. For example, this is the heat exchanger for compound D, which is benzene. So for this equipment, the user have to select type of heat exchanger first. I will select double pipe heat exchanger and then click OK. So next will be for the deciding parameter. In here, user have to insert the material, but I will set the carbon steel as a manual. As a default, and then the pressure will be indicated based on the operating pressure of this heat exchanger. And next is the area of heat exchanger that user can change the value. And after we fill all of the information in here, the process cost will be calculated. Then I will click OK. And next is the utility information. Since this is the unit that requires cooling utility, so I will select cool utility. And it will use the process cooling water. Then user insert the heat duty that we got from step 8 and click OK. So here is how to insert the information for one of the equipment in the process. But in the real case, user have to insert every information for every single equipment by using this tool. Then after we already insert all, it will report first the annual price for the raw material and the annual price for the product. And next is the purchase cost of the equipment, such as the heat exchanger, HXOD in here, and the utility cost of the heat exchanger will be calculated also based on the option that I have selected before. But to saving the time, I already insert all of the information and generate the output file of the econ tool already. So I will call this one. And import the HDA econ output file here. And after we import, there are 4 types of information that econ have given. First is raw material and product. We will calculate this based on the flow rate of inlet and outlet stream from step 8. of the result that we import from Pro2. And second is purchase and utility cost data for equipment, including the selected flow sheet, will be calculated based on the utility data. If we click here, pie chart of each cost in each unit compare, so user can obviously see the significant proportion of the cost. And next, after the equipment costs are calculated, we will combine with other manufacturing cost and the working cost. As the same, it can be plotted by clicking here. Yes, and user can compare. And lastly, from all the previous data, the econ will also give the rate of return, the payback period, and the other important economic evaluation. Also, the cumulative cash flow will be shown here, and the user can see the break-even point that will be useful for the investment and compare it with the other alternative. So in this case, for example, the break-even point is about 4.5 years. And next, going to step B, the sustainable analysis that was calculated a selection of the sustainability indicator through the sustainable in the ProCAFD. So starting with select the main product here, I will select benzene, and here waste will be biphenyl. And then from the result of step A, I have calculated all of the cooling, of the energy utility and the electricity utility in here. And then after we select the product, the flow rate will be filled in here based on the same summary. And from the Pro2 result, I have calculated the water required in this process. It is approximately 550,000 kilograms per hour. And then I will click calculate. And the sustainability index will be indicated in this table. Next, step XC will give the information on the state of environmental and its impact on the human being, the ecosystem, and material. The environmental indicators such as potential environmental impact, the human toxicity potential, the global warming potential, and the other indicators are calculated based on the flow of inlet and outlet of the process. And in the last column, if it is in the green color, it means that the indicators of the inlet are equal or higher than the product. And in the opposite way for the red color. So in here, if user does not import any result in the step A, we can also calculate it through mass balance that we have shown in step 6. Okay, and next, also for the further environmental parameters that can be analyzed, the footprint values are available through linking with the LC SOP. So there are 3 types of footprint. First is the ecological footprint that measure and compare between human demand and the natural resource available. There are numerous of areas that ProCAFD have given. And it can be calculated in 3 units here. So for example, I will select, let's say my country, Thailand, with GHA per person, and then click calculate. And we can select more than one country, like I select Denmark here with same unit and click calculate. So in this box, user can compare the footprint between each area that they are interested. And this ecological footprint will divide to land use, the build up land, the carbon cropland, forest product, and the other footprints. And second, the water footprint that measure the amount of water using by the human activities or the volume of water that are consumed or polluted. For each water component is specified by the different source of water that are consumed. At the same, we have several options of the area in here. And user can select T-try depending on the source of water. So in here, I will select Thailand with agriculture and calculate here. And Denmark. So after we calculate, the result will show in both yearly average and the data in each month separately. And lastly is the carbon footprint. So in this part, the equipment that require heating duty and the electricity will be listed in this table. There are multiple of utility source that can be selected. I already have set it as a default value, but in here, user can select several source. Yeah, we have several data index that can be combined. And then I will click calculate. So now of the carbon footprint of each unit operation will be calculated and shown in this column. And next. Okay, so for the last part of the analysis, since an inherently safer design is one of the avoid hazard instead of culturing them, particularly we will try to reducing the amount of hazardous material and the number of hazardous operation in the plant. So the inherent safety index for both chemical and process will be given in here. But when user go to this tab, the ProCAFD will update the property data from the property database that given the important property that are considered in the inherent index, such as the fat point, the boiling point, or the toxicity limit in here. So when user come to this page, the data will be programmatically searched and updated in this table. And then I will go up again. So first, user need to select which reaction they will consider as a main reaction or side reaction. And I will select reaction 1 as a main reaction and reaction 2 as a side since it's produced by phenol. And then select the material. I will select carbon steel. And for the operating condition range, it will be selected based on the stream summary in step A. And there are some important data that need to be defined, like the chemical interaction. In here, I will select explosion. And no data for process structure. And since there is a reactor, so I will select air-cooler reactors. And lastly, we need the storage tank for our product. So we select atmospheric storage tank. Okay, so here after all of the data and requirement are inserted, I will calculate it by click calculate. And all of the score will be calculated. The last column is the total number of chemical inherent safety index. And this will be the total number of the process inherent safety index. And the summation of the inherent safety index will be shown in this box. Okay, then next is step 9. So the objective of this step is to compare the utility consumption of step A. Then both, okay, I will click both overall Yes, then both hot and cold utility are showing in this table and in this figure. Utility cost will be taken from the step A, and energy will be taken from the step A, and the carbon footprint will be taken from step analysis footprint. And then with all of the analysis that we have done, it can obviously see that the compressor, which is PCORAB, have the highest utility cost and the highest carbon footprint in here. Since they have high capacity due to the electricity that are needed to be used, and as well as the heat exchanger in here, the heat exchanger HX2ABCDE, which is the heat exchanger after the reactor. It have the highest utility, but it is the cooling utility, which releasing the energy. So if we have a look in the utility cost in here, for this heat exchanger, it will be cheaper and there is no footprint releasing in this carbon footprint data. So we will consider in the heat X before the reactor, which is HI1 IC and HI1 RC, which is used for the inlet toluene and the recovery toluene. And these two are the ones that take quite significantly high utility, as you can see in here, and also release significantly amount of carbon footprint. And subordinately, the column also can be considered in here. But the column can be considered because the labeler, which was used for bottom product, especially the last column, which is column that used for the toluene and benzene separation. So in this column, there are very high reboiler duty and carbon footprint comparing with the other distillation column. So if we want to target the improvement of this process, we need to do in these three units that releasing a lot of footprint and have highest utility cost. So next, I will open the presentation. So this is the flowsheet that I have generated before. So to be more clearly, if we have a look at the flowsheet that generated by Pro2, the heat after the heat egg before the reactor of the compound C, the inlet, and for the recovery. And the distillation column, which was used for the toluene and benzene separation, and the compressor for the unreacted AB stream. Yeah, so these 4 units can be considered. And then in order to reduce the compressor duty, something needs to be done with the first unit for reducing the flow rate of the compressor, as well as in the distillation column. If feed flow rate are decreased, the reboiler utility can be decreased also. And for the heat exchanger, the heat integration can be done in the further step of the ProCAFD, and this will be shown in the next session of the webinar 1, along with the improvement of the further process optimization and integration. But anyway, in the heat integration, there are one modification that we can immediately done to get the less utility. So as I have mentioned, the heat exchanger. So as I have mentioned, the heat exchanger before the reactors have combined to be one heat exchanger. It will combine the inlet the heat exchanger for the inlet compound C, the heat exchanger for AB, and the heat exchanger for the recovery unreacted reactant. Okay, So in here, there is the heat exchanger before reactor and the heat exchanger after reactor. As you can see that this heat exchanger will require a lot of heating utility, and this heat exchanger will release a lot of energy. So the stream before reactor and after the reactor can be considered to exchange the heat in the heat exchanger. That's why the heat exchanger X will be added by using the hot stream as an output of the reaction here, and using the cold stream as an input of the reactors. Also, the heater and cooler also still be used to compensate the excess utility that cannot be exchanged in the heat exchanger. Okay, so from the heat integration that we have developed, in the heater one, the utility required was reduced to only 800 millijoule per hour, as well as the cooling utility of the cooler after reactor that was reduced to only 7,000. And the heat for the heat X unit that we have added, the utility that are exchanged is about 20,000 millijoule per hour. Okay, so despite the several simulating and analysis steps that I have demonstrated, ProCAFD have defined the detailed information of the consider process synthesis problem and determine the safety, economical, environmental, and the sustainable information leading to the process development of the given detail. And one of the ways to improve process are demonstrated in this presentation. But all in all, this is just initialize of process innovation and modification that we can that can be done in this process. So I hope you will stay tuned for our next webinar session, and we can continue the further parts of the process development tomorrow. Thank you for your attention.
Okay, thank you. There are some questions. Since there are not, maybe if you in the Thai office unmute everybody, maybe they can ask the questions directly. Is it possible to unmute everybody, or at least Nisha number 18?
Yes, we can unmute Nisha number 18.
Participant number 18 is Nisha.
Hi, can you hear me? Yes.
Okay, do you want to ask your question? And also there is one more person who has asked a question. Try to unmute all of them who has asked questions so they can tell them, ask the questions directly. Okay, please go on, ask your question.
Thank you so much. It's really interesting work. I was waiting from yesterday. My question is that I have seen that with your simulation, you have one place where you are trying to have the inheritance safety, which is showing some data. But my question is that if you, for example, you are inserting some temperature or some kind of parameters which may draw to some accidents, so do you have some alert system either by calculating, after calculating, or before calculating to show that it might be having some accidents?
It's a very interesting question, and we don't have it now, but some people have been asking us to develop a kind of a monitoring system. So if they want the monitoring option, that would be the best way to add that. But otherwise, what we are thinking of is to put upper and lower bounds on the sizing parameters, including the temperature, pressure variables. So if during the design calculation or the analysis calculation, we reach a value outside the bounds, then it will give a warning. But at the moment, we don't have the alert system, but it's a very good idea. Thank you for this idea. We will try to see. Not everybody might be interested in that, so our option may be that if somebody wants the monitoring system with alert, we will do that for them.
Thank you. Thank you.
Next question. There was Dr. Shilpa, number 66.
Yeah, good evening to everyone. Thank you, Doctor, for this opportunity. My question is, when the demo was given by Konkana, the Pro2 simulation was more of a steady state kind of simulation. So is there any provision to switch to a dynamic simulation or to add a control strategy which will align to Nisha ma'am's question, where we can go for alarming or pre-alarming situation studies?
Yes. Again, this is an interesting question. The thing is that we have a separate toolbox for design and control that we are developing, because if we put also dynamics and control into this tool, it will be too complicated and not many people will be using the main options. So our idea is that this will be steady state process design optimization sustainability, but one of the designs from here can be taken into a new toolbox, which is integrated design and control. And then it will start with the dynamic model and operability issues and design the controller and do the closed loop control, maybe including monitoring. So that's the idea here. And also the design of the system, what we are trying to show in the design and control is that the distillation columns that are designed at the highest driving force, we are showing that those designs in dynamics, in operability, in safety is also using the minimum energy and is the best controller that can be obtained.
Thank you for the answer.
Anybody else? I think there is one more question or more. Number 142, Shekhar. Participant 142, Shekhar, can you make him, unmute him?
Okay.
Yes, sir. Sir, I want to ask something, sir, for a certification course first, for that. Hello?
Yes.
Yeah, I couldn't understand your question. Maybe I will read it. I want to ask any kind of certification course, basic or advanced level in the future. Yes, it is possible. We can think of that. We also give courses directly for some universities. So, but depending on whether your university would give it or whether you would like to take a certification course from us, we can look into that. Did I answer your question? Okay. Are there more questions?
No, right now.
So one thing that again, I'm sure there are students in the participants, there are researchers, there are people from industry. What you can see with this tool, that a process design from starting from zero, only knowing the chemicals we want to use as raw material, to the product we want to make. From that point, to a completely analyzed process, it can be done very, very fast and very reliably. So for those who work in the industry and research, they can get their results very fast. But in education, I'm not sure whether I want to release this for education purposes, because students will finish their design project very fast and not learn too much. So I'm hesitating to release it for education purposes, but for problem solving, yes, it would be something that can save the person's time quite a lot. What do you think? For those who want to, the responsible teacher of the course, if they want to use it, that's fine with me. But they should not give it to the students, because the students will finish their project within one day instead of taking 3 weeks or 6 weeks to solve. What do you think? If you raise your hand, we can unmute you. Yes, can you unmute Rodolfo, number 4? Oh, and 148. Can you unmute 148?
Yes.
Luis, you can say what you
Hello.
want. Yes.
I fully agree with you, Rafael, because I know that from the past, which we did with bachelor students, we gave them access to a software simulation tool. It was Unisim, and they started simulating without thinking. So it became really number pushing. And they did not look at the results that came out. So I agree with your comment. So careful, you should give it to students who are at least done it by hand once and know what is all behind this.
Yes, exactly. I don't want students to blindly use the tool and then say, okay, here is the result, and they don't really learn anything. So maybe teachers like you can have it, and then you can direct the students in the right direction.
Yeah, and what would be really interesting is to use it maybe for a master assignment. This kind of thing.
Yes.
Usually students have then finished the design course, the regular design course, and then are much better experienced, higher level, and then with this they can do a really next level design.
Yes.
But thanks for the session. It was really interesting to see what you can do with the program.
Thank you. Anybody else has comments? Okay, then this has been a long day. Oh, there is one. Nisha, number 18. Can you unmute her?
Yes, you can speak now.
Okay.
Sorry, I'm taking your time again. Actually, I'm partially agree with your statement to not share it with the students, because I am a student myself, but I'm in PhD here, Bangladesh. And I think that someone like me who's trying to develop something more on the top of what is already available. So we must need to know actually that what are the things available, rather than we blindly develop something and it's already available. On the top of that, we really need to know that what are the missing links so we can improve somehow. So I think that we really need to grab opportunity to see what's happening.
Good. And Rodolfo, you want to say something?
Yes, I agree. Luis said some things already. Being in the industry, you can see lots of young people that come and they know how to use simulation softwares, and all the tools that we have available right now. They have increased a lot in these years with facilities in computational efforts and all. And they they are not critical about the results that they have, and they just do that and put, okay, yeah, it's in the simulator, so it's fine. No. And well, why did you choose this software package, for example? Well, I don't know. I decided to. So yeah, you don't really know if this is true or not. So it is important to try. But I agree with him. For master's or doctorate students, it may be something more interesting because they are already a step ahead in their pursuit of knowledge, and also that can be helpful for them to make things faster, you know. But yeah, it's complicated with new students. I was one not so long ago, but I'm very critical, so that's it.
Mm-hmm. Yes, so that's why we want to help people who want to solve problems very fast and reliably, so they can do more things at the same time. Yeah. And then for education purposes, I want to release it together with the teacher who would teach the course. So then they can explain to the students why some decisions has been taken and not do blind trial and error kind of projects.
For sure. It's better in a general manner. Thank you. Thank you. It was a very nice day.
Okay. So tomorrow, we look forward to seeing you tomorrow. This will be quite exciting. Professor Stratos Pistikopoulos will talk about his synopsis project, which is about process intensification. And I will also give our view of process intensification, but process innovation is not just process intensification. There are many other things that can be done. So we will give you an overview. And thank you very much. And wherever you are, have a good rest of the day or night. See you tomorrow. Bye-bye.
Thank you.